Hi everyone. Today we are doing chapter 7.3 on unions and intersections. So in addition to being concerned with how one event might affect another, that's independent or dependent events that we talked about in lesson 7.2, it's also useful to be able to calculate the likelihood of two events happening at the same time or the likelihood of satisfying at least one of a set of conditions. For example, let's pretend you're at cruising Match.com for a potential date and you're choosing attributes in a partner that are important to you. So in class we came up with a list of attributes and then we chose two that we wanted to work with. So one of the good ones was people who have a sense of humor. So let's let event E be a person who would say they have a sense of humor, or they consider themselves to be funny. And then let's let event F be someone who considers themselves to be generous. So we've got sense of humor and generous. It's going to be useful to investigate the set of people that are E and F. So this would mean they are both funny and they're also generous. But you might be willing to settle for just one of these attributes. So that would be a search for people who consider themselves to be funny or generous. Extra O there, generous. Or maybe they're both. Maybe we luck out. So when we do the search for people who are funny or generous, event E or F, it's going to be all the people that are just funny, all the people who are just generous, and all the people who are both when I do that search. Let's look at different synonyms for notation. So when I'm dealing with an and, I'm going to use this symbol here. So I would say E and F. I wouldn't write out and. It's also called an intersections, and it means both of them are happening at the same time. I'm sure you guys are all familiar with Venn diagrams from past math classes. So let's say I let this circle represent the pool of people who satisfy event E. They are funny. And then let's say I let this circle represent all of the people who are event F. They consider themselves to be generous. The people who are E and F are going to fall here where they overlap. These are my people who are funny and generous, right here. Now with an or statement, I'm going to use this U. It's called a union, and I would write E and then this symbol F for E or F. It's a union, and it's one, the other, but maybe both. So same circle in the past. Let's let this first one be all the people who are funny. Let the second one be all the people who are generous. And when I do my search and I pull all the people who consider themselves to be funny or generous, it's going to pull all of these people here. These are my people who are just funny. It's going to pull all the people from here who consider themselves to be just generous. But it's also going to pull my intersection here, all the people who are both funny and generous when I do that search. So notice when I have my intersection, I'm only looking here at the overlap. But when I'm pulling an or statement, I'm pulling every single person that's in this Venn diagram. Cancel. So sometimes, let's consider the students from an advisory group. And this is actually from an earlier problem set, so you've seen this before. So here I have 10 students. I've got, I believe it's 10. Adam, Anna, Celeste, Kim, Lucia, Miguel, Ming, Sebastian, Sylvia, and Thomas. Here I can see that I have 1, 2, 3, 4, 5, 6 that are picked for a varsity sport, and I have 3 who have been picked for honor roll. Here let's use a Venn diagram and fill in all the people here who are varsity sport. This circle is going to represent all the people who are on the honor roll. And remember, my intersection here are going to be all of the people who are on both here. So go ahead and pause the video and write your names where you think they belong. You'll recognize there's going to be people who are not on either one of these items. So let's draw a box, and we'll write the names of the people who aren't part of my Venn diagram here in my box, because they're in my advisory, but they are not going to be in any of these circles. So let's pause the video and fill out this Venn diagram, and then come back and check your work. Okay, welcome back. So here are the names you should have in your Venn diagram. You can see you've got Anna and Kim. They are the only two who are in this advisory group. They are also picked for varsity sport and honor roll. Thomas is only on the honor roll. Adam, Celeste, Miguel, and Ming are picked for varsity sport only. And then Lucia, Sebastian, and Sylvia are in the advisory group. However, they are not picked for a varsity sport or for honor roll. So that's why they are here in the larger rectangle area. So what I want to do is I want to calculate the relative frequency that someone is on a varsity sport and they're on the honor roll. Now, since I have done my Venn diagram already, I can see that 2 out of the 10 students, or 1 out of 5, or 0.2, 20%, of the people from my advisory group are varsity sport and honor roll. This is small enough to count. Now let's find the relative frequency that a person from this advisory group is on a varsity sport or on the honor roll. So here I can count. If I'm just counting up the people that are in my Venn diagram, I can see that I've got 4 plus 2 plus 1, which is 7 out of 10, or 0.7, which is 70% of people in this advisory are on varsity or on the honor council. So let's investigate a little question. Does the relative frequency of those who are on varsity or honor council equal the relative frequency that someone's on varsity plus the relative frequency that they're on honor council? So this is my question to y'all. Is this a true statement? Well, let's calculate it, because I know that the relative frequency of varsity or honor, I keep saying honor council, but it's honor roll, I'm sorry, honor roll. Varsity or honor roll is 7/10. So if I calculate the relative frequency that someone's picked for a varsity sport, that is 6 out of the 10 students in this advisory group. If I calculate the relative frequency that someone's on honor roll, that is 3 out of the 10. When I add these up, I get 9/10, or 0.9, and that is not 0.7. So no, this is not true. If I'm calculating an OR statement, I cannot just add up the relative frequencies, or the probabilities for that matter, of event 1 plus event 2. And the reason for that is when you add these up, when I try it this way, when I calculate all of the 6 that are on varsity sport here, plus all of those here that are on the honor roll, we double counted Anna and Kim here. We counted them with my first one with the 6/10, then I counted them again with the 3/10. So therefore, this formula here is not going to work. It's going to have to be adjusted in some way if I'm wanting to think of a formula. So let's learn the formula for and, the formal rule for and. So if I want to calculate the relative frequency of event V and event H happening at the same time, all I need to do is calculate the relative frequency for event V, my first event, and then multiply that by the relative frequency of the second event happening, which is H in this course, given that the first event already happened. So I'm going to have to use that conditional probability that we learned. Let's take a look at this within context of my problem up here so I can see that it works. Here it was easy to count because I only have 10 students and I was able to make a Venn diagram, but sometimes you don't have that. Sometimes we don't have this much information. So let's fill this in. The relative frequency of V, someone in my advisory being on a varsity sport, is 6 out of the 10 students, times the relative frequency of them being on the honor roll given that they were already on the varsity team. So since I have this given that they were on the varsity team, I'm no longer pulling from my whole advisory. I'm only pulling from the 6 here, up here, that are on a varsity team. So of those 6, how many are on the honor roll? I can see Anna is on the honor roll. Check her off. Kim is on the honor roll. And let's see. That's it. 2. 2 out of the 6. When I multiply these, notice how this 2, let's do this, my bad, leaving me 2/10 or 1/5 or 0.220%, which is the same thing that I had up here when I was calculating it just using my Venn diagram right up here. So here when you're doing an and statement, the order does matter. It also works with probability. So if you wanted to write a formal rule for probability of event A and B, you would say that's the probability of A times the probability of B given A. It's worth noting that while the order matters here in my formula, the probability of A and B happening, it's the same thing as the probability of B and A. This is commutative. So here I would just say that's equal to the probability of B times the probability of A given B. You just got to pay attention to what you're given in the problem, what you have access to, and what you can easily calculate. If you can't calculate these conditional probabilities, it might make sense to take a look at use the commutative property to flip those around so that you can calculate what you need. All right, so that's an and statement rule. Let's look at this chart. Consider the relative frequency to a table that displays students who consider themselves short or not short and report that they have been bullied or that they have not been bullied. So here I've got this two-way table. My first question is, what does 0.34 represent? This right here. So 0.34 means that 34% report looks like that they have been bullied. If I'm reading this right. What does the 0.44 represent? Here. So that means 44% report to consider themselves short. And now what does this 0.20 represent in the table? So here we can see that 20% is where the column for those who say they've been bullied and the row for those who consider themselves short intersect. So that means 20% report to be short and bullied. My next question is, what percent of those in the survey report to be short or bullied? So right now I'd like you to pause the video, contemplate that question, come back when you are ready, you think you know, and let's see what you think. Okay everyone, welcome back. So in class, there were two main ways that I saw students approach this problem. Probably the most popular way was to consider all of the people who report to be short. And so they said, all right, I've got 20% here and 24% here who consider themselves to be short. So they definitely have to be included. But I also want to include the people who are bullied. So I'm going to go to the no short column, and I'm going to go to no short row, and I'm going to go to the yes column for bullied. and look at this 14%. I want to make sure I include them too because they are bullied, so they satisfy. And then the 42% that say they're not bullied and not short, I'm not going to be including them. So when I add these up to calculate what's the relative frequency of short or bullied, I'm going to add up 0.20 plus 0.24 plus 0.14. When I do this, I get 0.58, or 58% of those who were surveyed reported that they are short, consider themselves to be short, or they have been bullied before. And so that was one way that students approach this problem. Another popular way that we discussed was people who said, all right, I want all the people who are short or bullied. So I need to add up all the people who are short here. So I'm basically adding up these two numbers to get 0.44. And let's add up all the people who are bullied. So my big numbers here that I'm adding up are these two numbers. So I'm saying relative frequency of short or bullied is going to be this 0.44 plus the 0.34. However, when I did that, when I added those up, I double counted those who reported that they are both short and bullied. So I need to make sure I subtract out that double count. So whenever I do this, when I add up the 0.44 plus the 0.34, I get 0.78. Subtract that group that I double counted, and I'll get the 0.58 or the 58% again. So those are the two ways that we saw when I gave this problem in class. Whenever you're looking at a formula or a formal or statement formula, it's usually that second method that we see, because a lot of times we don't have all of this information that this two-way relative frequency table has given us. Sometimes we only have the specific data that I need. And so if I'm writing out a formula, this method, the second method, is used most often. So if I want the relative frequency of short or bullied, I would say calculate the relative frequency who those consider themselves short, plus the relative frequency of those who consider themselves bullied, and then subtract the overlap, which is the relative frequency of those who are short and bullied. And what's great about this formula is it gives me 4 different variables per se. And if I have 3 of them, I can solve for an unknown as long as I've got 3 of those 4. So that's always pretty neat. This also works for probability. So if you are going to write, what's the probability of event A or event B? Well, it's the probability of the first event A plus the probability of the second event B minus the probability of event A and B. All right. Visually speaking, when we're looking at this OR statement here, what I have first is I've got, let's assume this is event A and this is B. So here I'd have probability of A plus the probability of B. Notice that the intersection is a little darker color because it's been added twice. Here what I have is the probability of A and B, that intersection. I need to subtract that out so that now I have the probability of A or B. And notice now there's no discoloration. You can see it here. This has been counted twice. That's why it's a little darker. Now sometimes it's easier to consider the complement, especially when I'm trying to calculate OR statements. So we found that the relative frequency of short or bullied was 58%, or 0.58. What is the complement of short or bullied? So the opposite in a way. So if it is short or bullied, the opposite would be not short and not bullied. So this line here is what I'm using for not. Some people will use like a tilde sign, something like this for not. I've seen that before as well. So if I want to calculate the relative frequency of not short and not bullied, so what I can do is I can take the complement rule, which basically says that if two things are complements of one another, that they have no overlap at all. And if they have no overlap, that means I have to account for all of the outcomes. And so if I'm accounting for all of the outcomes, that means I just have to take 1 minus 0.58, since I know that short or bullied is 0.58. So that would just give me 0.42, or 42%. I mean, I can also read it off my chart. It's easy to see whenever I consider that first method that the students used when they were doing the OR statement. When they were adding these up, they added these two numbers and this two and that one number to get the 58%. That only leaves 42% right here for all of my other outcomes. All right, and we're going to talk about complements more. Right here, I've got a formal definition. So if two sets together cover all possible outcomes and there is no overlap at all, they are called the complements of each other. So you can see, I think this actually works well with my advisory group example. So in my advisory group example, I had 7 students who are in varsity or on the honor roll. And then outside of that Venn diagram, remember in this like blue area right here, I had 3 students who weren't on either. So being on varsity or honor roll is the complement of being on not being on varsity or not being on the honor roll. They would be complements of each other. So just one more time with a visual of my short and bullied. If I want to calculate the relative frequency of not short and not bullied, that was my 0.42. Plus the relative frequency of short or bullied, that was my 0.58. When I add these two together, I should get 1. And that is because these are complements. And together, if I add them up, they have to account for all possible outcomes. So before we're done with the lesson, we're done learning new material now. All I want to do is summarize all that we've learned and all of the formulas. And I'm using probability here since we primarily focused on relative frequencies with data we could use throughout the lesson. So for my AND rule, if I want to do the probability of A and B, that is equal to the probability of A times the probability of B given A. And if I don't like the order of these events, this is commutative. So the probability of B and A is the same thing as probability of A and B, which would mean I have the probability of B times the probability of A given B, if I prefer that order. For an OR statement, the probability of A or B, that's going to be equal to the probability of A plus the probability of B. But oh, don't forget to subtract out that overlap. So minus the probability of A and B. If you want to make a note to yourself here, this is subtracting out the overlap, what was double counted. And next, my complement rule. So my complement rule, and let's define a complement too. Every outcome that is not in event A is called the complement of A, and is denoted not A. And then, I mean, I've also seen like A with a bar over it. I've seen AC for a complement. I've seen tilde A. I've seen these in various textbooks throughout my career. I'm going to use this one right here in class for the complement of A. So there's a few different ways that you can manipulate our rule, but our big rule is that the probability of A plus the probability of not A is equal to 1. And I can manipulate this however I want. I can say the probability of A equals 1 minus the probability of not A. I can say the probability of not A is equal to 1 minus the probability of A as well. Those are my big rules. All right, so now you are all set. You know unions, you know intersections, you know your complement rule, and you are ready to go to problem set 7.3.